faster this one.
I'm just adjusting the angle so this way I can record without having to worry, whether I'm getting out of range or not. So cable management has room for improvement. This is casting a shadow on the paper, but otherwise good enough. Okay. All right. So what we'll do today is we're continuing with the discussion of floating point numbers. And what we'll do is to kind of focus on how do we parse a base 10 scientific notation first. Okay, and then, because there will be a homework assignment, it's not up yet, okay, but there will be a homework assignment on base 10 scientific notation parsing. Okay, so we'll have to start with parsing first, and then once we get the base 10 scientific notation parsed, then we can start the actual conversion. So I'll touch on the parsing part just a little bit today, and then we'll focus on the other parts later on. Okay, so with parsing, okay, so let me switch back to the notes here. So the parsing part has to do with this regular expression. Okay, this is a regular expression, and I think I explained that last time. Yes? Okay. So, if you don't understand or don't remember what the black backslash equal and stuff like that mean, just read it, okay? Because the bullet points right below this explains the regular expression itself, the syntax of the regular expression. You can also click on some explanations. That is a whole web page dedicated to the explanation of regular expression in VI. Okay. The cool thing about doing a regular expression in VI is easy to test. So you can actually write some stuff inside in the editor, do a slash, and then type your regular expression and see if the regular expression works or not. So it's really kind of cool. It is also practical. You may not have encountered a need to use regular expression in an editor when you're editing your programs, okay? But the question is, how long are your programs and how complex are your programs compared to what you might encounter in industry? So in industry, a lot of editors, even IDEs, still support regular expression because it is such a useful feature. So this is something that is not entirely related to related to assembly language programming, but overall speaking, it is going to be beneficial to you as long as you stay on track as a computer science major or computer engineering major. Is that okay so far? Okay. All right. So how would you parse something like this? If I were to tell you that everything is stored in a string or an array of characters that is null terminated already, how would you parse that string to recognize all the individual parts? And then what we want to do is to do something like this. So I'll give you an example because this is the best way to illustrate what you need to do. So let's just say that I have an example of 4.256 e minus 16. Okay, so this is the incoming. This is what is stored in the string. Each character is representing a particular item in this particular one. So how would you write a subroutine to do this? Now I can tell you what the end result needs to be. Okay, what you need to track. The first thing you need to track is the sign. The sign is easy. It is assumed to be non-negative unless you see a leading negative symbol here. If you see a leading positive symbol, just leave it alone, parse it, take it out, because it doesn't change the actual default value. So the sign is 1, and then the other part is the mantissa. Now the mantissa that I want you to track is an integer. In other words, I do not want you to use any double or float in your parsing subroutine. Okay, so there's no need to use any float representation. In this case, I want the mantissa not to be 4, but 4,256. In other words, it is almost as if the decimal point does not exist. You just parse the entire chunk. Now, the decimal point is definitely important. So the way we account for that is to say if I represent, so the sign is going to be a 0 because it is non-negative. So in this case, the exponent, okay, these are all in base 10, so I'm going to put a 10 after that. So the exponent in base 10 is not just negative 16, because negative 16 is what you see here, but we also have 3 shift operations that is implicit in order to turn 4.256 into 4,256. So each time we shift the binary point, okay, a decimal point in this case. So each time we shift the decimal point from here to here, from here to here, from here to here, the mantissa is 10 times the value of compared to before. But we don't want the value represented to change, right? So the only way to compensate for that is to change the exponent. Every time you move the decimal point to the right-hand side by 1 digit, you decrement 1 from the exponent. So in this case, just hold on 1 second, okay? So in this case, we have to adjust 3 times because we moved the decimal point 3 times. 1, 2, 3, and as a result, but even though it was explicitly expressed as negative 16, 10 to the power of negative 16, we have to subtract 3 more to adjust for the shifting. Yes, go ahead.
I was going to ask, is the recording?
Yes, I think it is recording with voice and it is streaming. There we go. Cool. Thank you for checking. Yep.
So is that -3 the excess?
The -3 is for adjusting the decimal point moving. So together, when you add up these two, you have -19 as the actual exponent.
Okay, is there any, so I'm guessing we're not dealing with excess exponents in this one? We're not dealing with excess in this example?
Excess? What do you mean by excess?
I know in my 440 class, the teacher would, for example, give us this, but then he'd say excess 4. So you'd have, for example, like our exponent is -19. Then if it's excess 4, you subtract 4. So that, maybe it's different.
There's no excess at this point.
Okay.
Yeah, because what I want is to represent everything in unsigned integers,
Okay.
so that we can prepare for the next stage.
Okay, so all we have to worry about is sign, mantissa, and exponent.
Yes, but the mantissa base 10 is an integer, and so is the exponent.
Okay.
Yep. So now your job is to take a character array, which is this, and turn it into something like that. The homework assignment is not written yet, but the first thing I would do is to use a structure. In other words, instead of using loose variables for the sign, one for the sign, one for the mantissa, one for the exponent, use a structure. The best thing about using a structure is encapsulation, which means you make a variable of that structure type, then you just pass that one thing around instead of 3 things around all the time. Okay, so that's why my recommendation is to turn it into a structure so that you can pass at least an address of that structure around easily. So, are there any questions? How do we get this done? Now, obviously, this part is parsing, which is not really a part of cisp310, assembly language programming. But since you have to do this, let's think about it, okay? Because you guys all have taken cisp360 already. And doing this only involves, the understanding of an array of characters, character comparison, okay, basic arithmetics. Yep.
Do we use ASCII values or?
Yes. So these were represented in ASCII values in an array of characters. So in order to convert a character into a digit that is a character into the actual value the digit is representing, how do you do it? Okay, so there are those things that you have to kind of think about. All right, so this is going to be the next homework assignment. It's not up on Canvas yet, but it will be soon. All right. So one thing you might want to do is to think about, how do I structure this code? Okay, you may not want to just sit down and start cranking out code right away. This is not one of those programs, where you can just kind of, okay, I'm going to sit down and do it. Okay, I personally would much rather break this up into tiny little fragments instead of using one gigantic subroutine to do it. I would have one subroutine only responsible for interpreting the sign, the overall sign. Okay, so one subroutine just to handle this optional sign here. Yep.
When you're referring to subroutines, do you mean the functions?
Functions, yes. Function, subroutine. Yep. So I would have one function just to deal with that optional sign. So this function has got 3 options, right? I'm not seeing a positive or negative. Fine, use the default. The default sign is 0, which means it's not negative. I'm seeing a negative. Let's make that a 1 because I explicitly see a negative sign. But then you also have to remember to move the pointer forward to basically say the first character has now been parsed. If you see a plus symbol, there's no need to change the default sign, which is a 0. But then you also have to move the pointer forward. In other words, all your parsing subroutine need to share a single pointer, which is marking which character am I reading. Where is the current point that I'm reading in this entire string? Is that making any sense? So make it part of the structure, okay, so that you're passing that structure around into the different subroutines. I would use one single subroutine to do this part, okay, which is a single digit. According to the regular expression, there's only exactly one digit before the optional decimal point. So this is pretty easy to do. Okay, you just read that digit, convert the ASCII code of the digit into the value of the digit, and put it into the mantissa 10 component of the structure, and then move your pointer forward to the next one. Is that okay so far? Okay. I would make another subroutine to deal with this part here, including the decimal point. So this optional part is going to be parsed by calling another subroutine. The first thing this subroutine is going to do is say, am I looking at a period? If I'm not looking at a period, there's nothing for me to parse return. On the other hand, if I am looking at a period, then I need to take note, because depending on how many more base 10 digits is after the decimal point, I need to make that adjustment to the exponent. Is that making any sense? So if you are in fact seeing a decimal point, then you go, okay, let's move that character pointer forward. So I'll be looking at potentially the first digit to the right-hand side of the decimal point. What if I don't see anything to the right-hand, if I don't see any digit to the right-hand side of the decimal point? My job is done. Okay, cool, not a problem. If I do, I got 2 things to do, okay? So if I see a digit to the right-hand side of the decimal point, I got 2 things to do now, because I have to somehow integrate that digit. Let me point out which one we are talking about. So we have to somehow integrate this 2, the digit of 2, so that the mantissa 10 is now 42. But I also have to remember there's an implicit shift of the decimal point to the right-hand side, so I need to compensate for that by decrementing the exponent from 0 down to -1. Is that okay? Yep.
Kind of a linear search in a loop?
It is a loop of some kind, but it's not a search. Okay, so the criteria to stay in the loop after you parse the decimal point is I'm looking at a digit. You can exit the loop as soon as you're not seeing a digit, because you don't know what to do with a non-digit for that portion of the scientific notation. Okay, so when you move on from 2 to 5, you're going to do about the same thing. You say, well, we have to shift. Okay, so first of all, you have to turn 42 into 425 at this point. Okay, and then the second thing you have to do is to say, okay, now we have 2 places to the right-hand side of the decimal point, so we have to adjust the shifting. So the exponent is now -2. Is that okay? Or not? Okay, so moving on to the 6, same thing. So you now turn 425 to 4,256. Okay? And then you have to remember, oh, I'm seeing 3 digits to the right-hand side of the decimal point, so now the base 10 exponent, exp10, is -3. Are we still doing okay so far with this example? All right. And not knowing the next character is an E, you move on to E, okay? You go like, oh, this is not a base 10 digit, I'm done. So you leave the pointer, you leave the character pointer on the E so that you remember this is the next thing that I'm supposed to look at. But your job to parse the decimal point and everything, all the digits to the right-hand side of the decimal point is done. And I'm gonna put that into its own subroutine so that it stays fairly short and easy to understand and easy to debug. Okay? When that subroutine returns, then you call the last subroutine. The last subroutine is responsible for the optional exponent part. So that subroutine, upon entry, will do one thing first. Okay, you can do it with a conditional statement and say, am I looking at a lowercase e? Because if that subroutine is not looking at a lowercase e, it's done. Okay, it's not a syntax error. If you see a semicolon, it's okay. It's just like, I don't know what to do with this, but I'm done. On the other hand, if that particular subroutine sees E as a character, then it knows, oh, I got work to do now. So you move the character pointer from E to the negative symbol, and now you need a local variable to track what is the actual exponent expressed by this portion. Because you already have an exponent 10, exp10, storing a -3 because of shifting the decimal point. So you don't want to mess with that. So you need another local variable to keep track of, okay, what is the actual value expressed to the right-hand side of lowercase e? Okay? So you need to look at this sign here, which is optional. If you don't see a sign, it is non-negative. If you see a sign, it can be positive, which means you keep the default sign. Or if you see a negative sign, then you are looking at something that is negative. So you have to track that. Okay, so this thing has its own local variable to store the sign of the exponent. After the sign, which is optional, then you can say, okay, what is next? Oh, we are expecting digits. So in this case here, we are seeing a 1. So you basically have to use a local variable to store a 1, okay? And then you move the pointer forward, and it sees a 6. So you will have to turn that 1 into 16. But we are not done yet, okay? So then you move the pointer one more time, which is here, which is beyond the actual number. There's always guaranteed to be a null character past the end of the string. But regardless of whether it's a semicolon, a pound sign, a slash, or whatever, it is not a digit. And that's all you need to know. If it is not a digit, my job is done. So at that point, you would recognize that the E itself is specifying a quantity of -16. You add that quantity to whatever is already in exp10, because that already has the offset due to the shifting of the decimal point. Then together, that becomes your exp10. Is that okay? I'm just verbally describing the pseudocode to get it all done, but using an example to illustrate it. So are we okay on these concepts? All right. So sometime today I will get the assignment done, a description done, and put it onto Canvas so that you guys can get started. But to think about the process, you can start right away. This is something you can do right away during lab time today, is to think of a strategy to do this. So the first one is, how do you turn 4 to 42, and 42 into 425, and 425 to 4,256? Okay, it's times 10 plus something, right? You need to track the sign. After the E, how would you do that? You need a flag to store the sign itself, and then parse the number, and then combine the sign and the number to find out the actual value, in this case -16, and then you have to combine the -16 with the -5, that -3, excuse me, that's already stored in exp10, to come up with negative 19. So are we doing okay so far with the parsing part? Yes?
So I have a question. Is it only for the negative exponent, or
It's only for,
like it's negative 16, right? What if it would be a bigger number? Is it only for the smaller numbers or bigger numbers?
it's for both. If you don't have a, if this is a plus, then you end up with 16 minus 3, so the end result here is going to be 13.
Is that why we would use? Yeah, makes sense. So it would work the same way.
It works the same way. Well, it's going to be the same. I would use the same subroutine to deal with both a negative exponent as well as a non-negative exponent. Okay? So you will have a lot of loops. Okay? You will have some conditional statements. Anything that is optional turns into a conditional statement. Anything that has any number of or at least one will turn into a loop. Is that making any sense? All right? Yep.
So e positive 16 will be optional here.
Sorry?
E positive 16.
Yes, that is optional.
But,
So the subroutine that you call to parse that, you have to call it. Except the subroutine may return right away because it is not looking at a lowercase e. So that subroutine go like, okay, I'm not, there's nothing for me to do here. Yep.
So the input's supposed to be a string? Or
Yeah, the input is going to be a string. And I can give you a template of what we can use. So I'll show you what the template would look like. All right, so I'm going to write a very simple program to parse a part of the command line into a string that will be passed to your subroutine. Okay, so assuming you're writing a single subroutine to return a structure like that, I'm going to give you the code that will give you the string. Okay, so this is not going to take long. So we'll go ahead and take a look at this program, and I'll just call this parse scientific notation, parse sci. Okay, and this is all in plain C instead of C++. Okay. So most of the time in your other classes, I think some of your professors may have told you that main can have parameters. Okay, how many people know that main has implicit parameters? It's just that most of the time we don't use them. Okay, some of you do. Very good. The first one is usually called argc, which is a count. Okay, how many arguments do we have? The second one is a const char star star, which is usually called argv. That's the actual argument. There are more, by the way, okay? But these two are the only ones that we are concerned with this particular program. So we stop here, okay? And in this case, I just have a return 0 right away for now, because I want to show you by the time I get to the return statement, what is in argc and what is in argv. Yes, go ahead.
Do you need the preprocessor statements or just going through
Nope, you don't need preprocessor statements whatsoever. Okay, so this program will compile, even though it doesn't do a single thing, right? I like programs like these, okay? Minimalist, but it gets the job done. Okay, gcc-g for debug information, -o to specify the output file name, the executable's name, parse sci.c, and of course, if you turn on warn all, it's always a good idea. Okay, there we go. And to make this program useful, you have to use GDB because you can run it by itself. It doesn't do a single thing. Okay, but when you do it inside GDB, maybe it does make sense. So we use GDB. Oh, okay. I have the GDB and then the name of the executable. You can now list the program. I put a breakpoint on line 3, which is where the return 0 is. Okay, and then I run the program. But then when I run the program, I'm going to run it with some gibberish after that. Blah 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 blah. Okay. So these are the things that will be on the command line. The R command in GDB is running the executable, but it also follows the very same convention as the command line. So if you have redirection, it will do redirection. If you have supply additional parameters, these will go into the program. Okay? All right, so go ahead.
So this is like a strategy for if you want to run it over and over to test it.
Yeah, it makes it very easy because otherwise you have hard-coded strings and that's not going to be very convenient. Okay, so we press the enter key, now we have stopped. But you can also see that main, breakpoint 1, comma main, blah, blah, blah. You can see argc is 8. we got 8 things in ARGC, which means ARGV 0 all the way up to ARGV 7 will have some kind of value. Does that make sense to you? Okay? Because this is telling us how many arguments do we have. This is telling you what the arguments are exactly. What do they look like exactly? Okay? So now we can do some printing. Okay? And I'm going to print ARGV first and see how smart GDB is. Not very smart, because it just tells us that, oh, this is an array of char pointers. ARGV itself is not a char pointer. It is the pointer to a char pointer, which can also be interpreted as an array of char pointers. Because remember that, right? Arrays and pointers are interchangeable in many contexts. Not all, but in many contexts, those two concepts are interchangeable. Which is actually why C is so dangerous. Because most other programming languages do not have that kind of concept. Okay, so if this is not what I want, I can just go through this. What is that? /temp/parse. That's the name of the executable. Okay, so the name of the executable is always the first argument. In other words, you don't have to parse that. That's not part of the actual useful input. Okay, so we'll take a look at ARGV1. That's F, which is the first argument. And this is the second one. And you can probably imagine the last one, which is ARGV7, is the last one, ASOI. Here we go. So this is how we can get to the individual parts of an argument in main, which definitely can come in handy. And of course, since most of you, are in a GUI generation, you guys would go like, why would I need something like that? Okay, because my program is a GUI program, so when I double click on an icon to start a program, these would be useless. Well, on the command line, this becomes very useful, okay, which is how you're going to debug your program for the most part. So now I can quit the debugger, go back into the program, and now I can do some checking. Okay, so I can say if ARGC is greater than 1, then I'll go ahead and proceed with doing more stuff. Otherwise, I might print an error message, I might do something else, but I'm not going to do any processing if ARGC is 1. Yep.
You don't even need to have the stuff in the parentheses for that, because it's implicit, right? So it's already there.
Sorry, say that one more time.
The argument variables, you said they're there even if you don't declare them like that, right?
They are on the stack even if you don't declare, but you have no handle to get to them unless you declare the parameters.
Okay.
Yep. If you declare the first one, you implicitly have a handle onto the second one, but that's really kind of ickish, to get to it using pointer arithmetic of a parameter to get to the next one. So that's why it's better to do it this way. Okay. So in this particular subroutine, okay, so I'm going to do my own here. So I might want to do a structure. Okay, so a struct parser. Okay. And inside the structure, I might have const char. So const char PTR is basically where in the string am I parsing, okay? And this is the right, okay? This is okay because PTR itself can change. The const applies to what it points to, not the pointer itself. Now, if I am going to do this, then we have a, well, actually, I think after the asterisk, right? Yeah, so now it would, now the pointer itself cannot change, as well as what it points to. If I do it like this, I cannot change the pointer itself to point to somewhere else, but I can change what it points to. Okay, so you have to remember all of these things that you should have learned in your C++ class. So this would be okay. And then I will have those things that we just talked about earlier. For the sign, you can just use an int if you want to. Mantissa is going to be an unsigned. And also for exponent 10, that has to be signed, so you have to use a signed integer. Okay. The range of the value of just a 32-bit integer is more than what we need for exponent 10, so we're not too concerned about that. For unsigned, for the mantissa 10, it's okay. You know, I just have to limit all the test cases that I can throw at your program, so that they can all, you know, be handled by a 32-bit unsigned number, because I don't know how you're going to write your program, or on what platform you're going to write your program. So I'm going to assume, you know, all the integers are 32-bit wide instead of 64-bit wide, which is fine. That's okay. All right. So with these things done, okay, then you write the subroutine. So this is a template. Okay. So the template is going to be, you can use an int, you can use a void. I'm going to use a void here, okay, because I'm not going to give you something that is not parsable, that you have to report an error. So you would just have, you know, this parse scientific notation in base 10, and you're going to give it a struct parser pointer, and it's going to do the rest. So write your code here. So from my perspective, all I'm going to do here is to say parse scientific notation in base 10, and I have to give you a structure first. So I'm going to declare a structure here. Give it some initialization. So I can initialize p.ptr to argv1. Okay, there we go. So that would be at the beginning of that particular string. Yeah, that should work. Okay. And I'll give you the address of P. So you are going to do your magic after that point. Is that okay? So I will save this file, okay, you know, as a part of your homework assignment. I will save this file and attach it to the homework assignment so you can start with this. But before I do anything further, it would be a good idea to compile this just to make sure that I do not make some stupid mistakes in this program, and I did not. Have not. All right. Are there any questions about the template of your program? So this is only for the first stage of converting base 10 scientific notation to the double representation. Yes?
I was thinking, why did you use int for sign?
Yeah. I can use a char, I can use a bit field, you know, it doesn't really matter. You know, it's either a 0 or non-zero. If it is a 0, that means the sign is non-negative. If it is anything if it's non-zero, it means the sign is 1, or the number is representing a negative value. Okay, any other questions? This is all good? All right, okay. So remember, write subroutines, okay? Theoretically speaking, you can stick all the code inside, write your code here, but that will make the subroutine rather long and rather difficult to debug. If you separate it into parts, it will make it easy to debug, okay? It will definitely be easier to debug if I were to be writing this program, okay? But since you're gonna write this program, you're gonna do whatever is gonna be making your job easier, okay? All right, are there any questions about this program? It's not going to be a very long program, by the way. It's a fairly short program. You just have to know what you're doing with each step, and debugging techniques is also important. Yep.
I'm thinking, since it's a constant char, it runs only one number each time the program runs?
Yep, you're only parsing one number. Whatever number is being passed to you from the command line is the one that you're parsing. Okay. Are there any questions about this one? So one thing you do not want to do is to modify main. So do not modify main. And I'm going to put a special label here too. I'm going to put a label here. Probably not here. Okay, I'll take this out into here and put a label here. Okay. So don't change the main program itself, because what I'm going to do is I will have GDB to set a breakpoint at L1, the label, and then at that point I can check what is inside the structure P. And that's how I'm going to check your program to see whether your parsing subroutine is working correctly or not. Okay, so don't change anything in main. There's no need for you to change anything in main. You have to put all your code into the content of parse sci10. You can add additional functions that you can call from parse sci10. Is that okay? So are we clear on the what you can do and what you cannot do? How do I know whether the program is working or not? It doesn't print anything. There's no cout, there's no printf of any kind. Use GDB, exactly. So you're going to use the same kind of technique that I'm going to use to debug, not debug, but to grade your program. You put a breakpoint at L1, you run the program with the parameter. By the time you get to L1, you check what is in P and see if P dot mantissa 10, P dot exponent 10, and P dot sign are correct or not. Okay, so I'll give you a dry run. How about that? Okay, I'll give you a dry run so that you know what you're expected to do. So I'm gonna put some useless code here, but just to make sure that we know how to debug the program. So I'm gonna say P parser points to sign is a 0. I'm doing a part of your homework assignment, by the way. And then P parser points to exponent 10 is also a 0. Okay. Reasonable, initializations, I would say. Okay, so exit the whole thing, compile the program. It complains about the label L1 is defined but not used, but that's okay. Okay, so this is one warning that you can just ignore because I don't like labels in any type of C++ program. This is only here so that I have a fixed point to debug, to check your code. Okay, so that's the only reason why there's a label here. So when you run the program, okay, you say gdb parse sci, and you put a breakpoint at L1. You can do it like that. Function L1 not defined. Okay, so let's see if is that going to work. Yep, there we go. So you can set a breakpoint of L1 in main by saying b main colon L1. Okay, so you can do all of this in GDB. If you are using code blocks, you will have to figure out a way to pass parameters using the command line. I don't know how to do it because I don't use code blocks. Is that okay? All right. Yep.
Can the file be created .cpp? I just saw this.
But that would make my job really kind of difficult because I'm going to use a script to compile your program and then use another script in GDB to grade it.
Because I heard you mention using flags to set some of the the period and stuff like that, or no, the sign at after E to use a flag.
Yeah, but you can use an integer. I mean, we got plenty of RAM memory here.
All right.
Yeah, so we are not gonna save 1 bit here and 1 bit there. Yep. Okay, so this is how you're gonna debug your program. So you say run and then give it a number like 23.678 E plus 25. There you go. Okay, so you're gonna run your program like this. Press the enter key and we are now at a breakpoint. So when you're at a breakpoint, what you need to do is now to say print. Oh, I cannot remember how I named that structure. P. Did I name it parse sci10? Is that it? Yep, I think so. There we go. So it prints a pointer. That's not what I want. There we go, P. P is the name of the local variable. So now you can ignore PTR. PTR is really just a pointer to the argument itself. So you can ignore that. But you need to check your sign. In this case, the sign is supposed to be 0 because the number is non-negative. Mantissa, on the other hand, is not supposed to be 0. Mantissa is supposed to be what? 23,678. Okay, that's what Mantissa 10 is supposed to be. And then exponent 10 is not supposed to be 0 either, because we have -3 or -3 because of the shifting of the decimal point, but we are subtracting that 3 from 25. So exponent 10 is supposed to be 22 in this case. So I would write a script in GDB to debug, to use the debugger to check whether your program, your parser, is working correctly or not. But it's going to be using this particular way, which means you cannot change the label L1 location, and you cannot change the names of the fields either, the members inside that structure. All right? And I'll just kind of make the restriction, that you also need to write this program in plain C and not C++. Which should not be a problem because C is a subset of C++. If you know C++, you know C already. And this program has no input-output, so there's no convenience issue of, I want to use C in or C out. Well, we don't have any input-output. Yep.
Are you going to have on Canvas the name for C?
Yes. Yeah, so I'm going to put this code onto Canvas. In fact, I can do it right now. Even when the assignment is not up there yet, I can still put this up first. So let's give a new homework assignment, or just a new file first. And this is going to be, what can I choose? File, there we go. Parse, .c. Okay. And now it should be, if you have a computer now, you should be able to see it now. Is that okay? So use this as a template, as a starting point, and then you just, attach additional code inside the subroutine itself. And I encourage the use of using subroutines because that really helps to structure the code, makes it easier to debug. Is that okay so far? Okay. So you can do this, gradually. Okay. So one more thing. Okay. I know most of you know this already, but I know someone is going to try to shortcut this. Try not to write the entire parse side 10 in one single session without debugging and testing. I would do it I would implement the part that checks the sign of the entire number and test the program. Make sure the sign is interpreted correctly. Okay, and then I'm going to write the part that only parses the first digit to the left-hand side of the decimal point, run the entire program, check to make sure that is done correctly. Okay, in other words, I would much rather go through more iterations of testing and debugging than to save time and go like, I'm going to write 200 lines of code before attempting to run it the first time or even compiling the first time. Okay, but that's just my personal preference. Okay, you don't have to do it that way. If you prefer to write 300 lines of code without compiling or testing of any kind, and then do one single big huge session of debugging and fixing all the syntax error and stuff like that, that's up to you. Okay, I cannot see how you do things, and that is certainly not a part of the grade. All right, I can only tell you what I learned from decades of programming. Whether that applies to you is a question mark. Okay, so are we okay on this? All right, okay. So getting back to my notes here. So the next topic we have to talk about is, let's just say that we have those mantissa 10 and exponent 10 done already. In other words, mantissa 10 is basically M10 in the notes. Exponent 10, exp10 is basically E10 in the notes here. So I'm assuming that you can get all that stuff done already. Oh, by the way, this is not adjusted yet because later on I talk about how we can adjust all of that stuff. So assuming that we have E10 done and M10 done already, sign is not really that big of a deal because it is going to be the same whether we're dealing with base 10 or base 2. So for the most part, we're not too concerned about the sign. But the real important part is how do we convert it from this into this? In other words, we have a mantissa that is multiplied to a magnitude that is specified as a power of 10. How do we change the representation from this into a mantissa that is multiplied to a power of 2 to specify the magnitude? That is the question. I want to preserve the value as much as I can, and that's why you can see that V is the same. Okay, so V is the value represented by this representation, which is your base 10 scientific notation, and this is the double representation. They're supposed to represent the same value. Are we doing okay so far with this part? You know, what we are trying to achieve. We start off with everything in base 10, and we have to convert it in base 2. Okay, all right. So the first step is something that we have talked about already, which is getting rid of the decimal point. So in this particular case, getting rid of the decimal point basically means, you know, we want to use 2.67 by itself is already in quote-unquote scientific notation. It fits the regular expression syntax that we just talked about. It doesn't have the optional sign to begin with. It has one single digit, a single, it has the optional decimal point and 2 digits after the decimal point. Does not have the optional e or the exponent part, but it is, you know, it does conform to the syntax that we need to parse. But when this is all parsed, it needs to be represented as this is your M10 or mantissa 10. This, on the other hand, is your exponent 10. So are we doing okay so far with this? You know, this is just another example to illustrate, you know, what values you should expect in mantissa 10 and exp 10 in your program. Okay. And I think I made a mistake here. I think this is supposed to be -2. I have no idea why I wrote -8 here. Let me fix that first, because I don't like mistakes, you know, just hanging around like that.
Take off the V from right as well.
Sorry?
Take off the V at the end of right. How would you write the scroll up, yeah, so a 5.1, getting right at the decimal point. Like getting after the V.
So it's like you read entirely.
Just a misspelling.
Where is the
Let's put the title.
At 5.1.
5.1 says getting right as decimal
Oh,
point.
getting right of the, okay. We'll fix that too, thank you. And this is 290296. Okay. Just look for right. And then we have the -8 here. That should be -2. There we go. We publish. And refresh. And voila. Fixed and fixed. Cool. All right, so now the question is, how do we do all that conversion? There are several concerns that we have to address first, okay? In this step, we need to apply a constraint that the ending M10 can be represented by a 64-bit integer. In other words, this portion needs to be something that can be represented by a 64-bit integer. And how can it not be represented by a 64-bit integer? In the scientific notation, if I give you like 2 point and then like a gazillion digits after that, that can exceed what a 64-bit unsigned can represent. So in your homework assignment, you don't have to worry about it, because I'm not going to give you something that can push beyond even a 32-bit integer. But if you're writing this commercially, you have to handle those, you know, special cases. So that means, you know, you have to make sure that when you're using this representation, the mantissa in base 10 has to be something that is representable by a 64-bit unsigned integer. So now the question is, approximately how many digits are we talking about? The slide here talks about how to guesstimate how many digits we are dealing with here. So we look at a 64-bit integer that is unsigned, okay? And as an unsigned integer, the largest value it can represent is 2 to the power of 64 minus 1. That's the largest positive value that an unsigned 64-bit integer can represent. But we are interested in how does that translate into decimal places, right? How many decimal digits are we talking about here? So the quick conversion is to basically look at this number, 2 to the power of 64, as this is 2 to the power 4, this is 2 to the power of 60, okay? So I'm just dividing into two chunks. One is the multiple of 10, and then the other chunk is whatever is left over. And then the part that is 2 to the power of 60 can also be rewritten as 2 to the power of 10, then to the power of 6. You guys learned about exponents in what? Middle school, elementary school? I cannot remember. Okay, but you know this, right? Okay. And then what we do is we do an estimation, because 2 to the power of 10 is 1024 or 1024, which is close to 1,000, and for approximation purposes, it's good enough. So that means we can replace this portion with 10 to the power of 3. So 10 to the power of 3, the whole thing to the power of 6 is 10 to the power of 18. And then plus the 16 to begin with, so we have about 19 decimal digits before we run out, ish. Okay, it's just an estimate. Okay, if you want the exact number, you can do the log thing and figure out exactly how many. But just by doing the quick math here, we know that when we have more than 19 decimal places for the mantissa, we could potentially run out of the value that we can represent as an unsigned integer in 64-bit. Okay, so that's that part. So the next thing is to get rid of the exponent of 10. In other words, in the conversion from something times 10 to the power of some power to something times 2 to the power of something, what we are really trying to do is to make this part 0. Okay? In other words, when we're in transition, as we are working our way to get to the solution, the value is preserved, but it is expressed as some kind of mantissa. I cannot tell you whether this is M10 or M2 because it is a mixture. Okay, it's just some kind of mantissa. But the power or the magnitude is now determined by two components. There's an E2, and we have 2 to the power of E2, and there's also E10, and then we have the magnitude of 10 to the power of E10. So these two exponents combined with this M is going to be the value that we want to represent. So we want to change so that eventually E10 becomes 0, and we are only going to use E2. This M would eventually become M2. Is that idea okay? I mean, does everybody understand where we are heading, what we are trying to accomplish? So initially, we have E2 being 0 because the original number is in base 10, and as a result, M is M10, and then we only know the exponent of 10, so that means the implicit exponent of 2 is 0 to begin with. So we want to change it gradually. If E10 was negative, we want to gradually increase it to 0 by changing E2 and also M to adjust for that, okay? If E10 is positive to begin with, we want to decrement it, but as we decrement E10, we have to make adjustments to M and also E2. But the idea is eventually we want E10 to be gone, to become 0. Is that okay or not? Okay. Any questions? Okay. If there are no questions, then we'll talk about a few more things, and then we'll talk about, we'll use examples. So there are two things we need to kind of take care of. Okay, one is to maximize precision, and the second one is to kind of get rid of any potential bias. Okay, so the next two paragraphs will talk about what I mean by precision and also what I mean by bias. Okay. When you perform this transformation, when you get rid of E10, eventually you will have to use divisions of some kind. Okay, you will have division by 2 in one case and division by 10 in the other case. But since we are only using integers to represent all of the things, mantissa 10 is an integer, unsigned, and then 10 is also an integer. But when you perform integer division, when you say n divided by d, and it's an integer with division, we are not representing the actual fraction precisely because we are losing the fractional part. Are we doing okay so far with that part? Okay, so integer division is automatically going to take the floor of the division. It's truncating the fractional part. Okay? So now we look at n, just like in this case, but this time we spell out n. Okay, we say that n is dq plus r. Now these specific letters are chosen because q stands for quotient, d stands for divisor, r stands for remainder, and the reason I use n is to make it the numerator. Okay, and d can also stand for denominator. Is that making sense so far? Okay. But since n is an integer, I can always express it as dq plus r for some kind of q and some kind of r. Is that okay so far? Okay. So now if I know that n is dq plus r, then n divided by d becomes dq plus r divided by d. That part is just expansion of n. But when you take this part, dq divided by d is just q all by itself, and then we have the remaining part, which is r divided by d. R is the remainder of a division, and d is the divisor, also the denominator in this case. R is always going to be less than the denominator in a division. Your remainder is always less than the divisor, right? So now so what we are losing, okay, by taking the floor function or by truncating, what we are losing is this part. This part is gone in a division, in an integer division. So if this part is a big portion compared to q, then we are losing a significant portion, okay, which is not good. So we want to minimize. We want to minimize the ratio, which is r versus n. This is what we want to minimize, is the remainder, the quantity of the remainder versus the quantity of n, which is our numerator. We want to make this as small as possible. You cannot control r, because r is the remainder, and the remainder, the range of the remainder is determined by the divisor. The divisor, you have no control over that because we have to divide by 10 or we have to divide by 2 in different cases. So since you have no control over the range of value of r, the only thing you can do is to control n. You can make n as big as possible so that this ratio is as small as possible. Is that making any sense? So instead of having something like 23 divided by 10, which is 2, but what you lose is more than 10% of the actual value, you're now saying, oh, what if I have 2300 divided by 10? Well, 2300 divided by 10 does not even have anything that you're going to lose, right? So let's say 2303 divided by 10. You're still losing, you still have a remainder of 3, right? But that remainder of 3 is a small proportion compared to 2300 itself. So as a result, your precision has increased. What if you make it 23,000,003 divided by 10? Then the portion that you're losing is even smaller. So what we're trying to do here is to minimize how much precision we are losing by maximizing n. Is that okay? All right? Okay. So the other problem about truncating is always making the values smaller. every single time we have an integer division, the result after the integer division is always smaller than what it is supposed to be. So when you do this repeatedly, then the actual value after all of these calculations will accumulate all of these errors, which are always erring on the smaller side. And that is called a bias, which basically means the value that you end up with is always end up smaller than what it is supposed to be. So a bias is not a good thing. So we want to get rid of a bias. So to get rid of a bias, we want to use a round function. The round function, when you apply it to d divided by n, is really, I think I flipped the symbol, didn't I? But that's okay, because it's still, the math still works out, but n is supposed to be the numerator and d is supposed to be the denominator. I guess I can fix it in the tool, but the discussion still stands. Okay, this part is still okay. So when you perform a rounding function, it is the same thing as adding 0.5 to the number before you truncate it. Let's see if that works. Okay, so we'll use the document camera to check out a few cases. Okay, so let's check out 0.2, 0.7, 0.6, and 0. Okay. What is the round? If you round 0.2 to the closest integer, what it is supposed to be? Supposed to be 0, right? So what do you do when you apply the other technique that we mentioned here? What if you add 0.5 to 0.2 first? You get 0.7, and you truncate 0.7, you get 0 back. Okay, cool, that works. What about 0.7 itself? When you round it, it's supposed to go to 1. When you add 0.5 to it, it becomes 1.2, and you truncate 1.2, it becomes 1. Very good, that works. 0.6, well, let's make it trickier. Boundary cases are the ones that we want to test, okay? So when you have 0.5, when you round it, you're supposed to get 1, okay? 0.5 rounds up to 1. And everything below that rounds down to 0. When you add 0.5 to 0.5, you get 1. And then you do the truncate on 1, you get 1 back. So that works. The other boundary case is 0 itself, okay? 0 rounds to 0, okay? Because it's already rounded to begin with. So you add 0.5 to it, and then you truncate it. 0.5 truncated is just 0 itself. So, it's not a proof, but it does illustrate, how the mechanism works and how it works for all of these particular values. Is that okay? So adding 0.5 before you truncate is the same thing as rounding. Is that okay? All right? Okay. So that by itself is not very fun. It's not very significant. But what we can do here is to say what we are really trying to round is the result of a division. The division, in this case, okay, I flipped the symbols, but it's at least self-consistent. So we're dividing d by n, okay, and we want to perform a round on this one. So we know it is the same thing as whatever we are trying to round plus 0.5, okay, that part we know. But now we know that since it's a division, we can now say, oh, but it would be the same thing as d plus half of n, and then the whole thing divided by n, and now we can just truncate it. Is everybody, understanding this math here? Okay. But this is good, because now we can say, oh, it's just an integer addition and integer division, because an integer division automatically truncates. So we don't really need to invent our round function. We can integrate the rounding by just adding a constant to the number that we are dividing. Is that okay? All right. Now the division, the divisor that we are going to use is either 2 or 10, which is really lucky for us because that means 0.5n is either 1 or 5. Because both 2 and 10 are divisible by 2. So that makes rounding very easy to do. All right, so now we're going to move on to the actual logic of what if exp10 is less than 0 to begin with. Then what we want to do is to gradually increase it to 0. Then we have what we want, right? So how do you do that? How do you increase E10 by 1? In order to increase E10 by 1, you have to divide m by 10 because we want to represent the same value. Increasing E10 by 1 is multiplying the value by 10. in order to compensate for multiplying the value by 10, we can also divide m by 10. That would compensate for the increase of exp10. Is that okay? So I didn't spell all the math here, but it doesn't hurt to spell all the math. So what I'm really saying is this part here. So we got m10, or some m, okay, just m here. So we have some m multiplied by 10 to the power of e10. That's what we begin with. But isn't that the same thing as m divided by 10 times 10 to the power of e10 plus 1? That is what I'm getting to. Okay? So when we increase the exponent of 10 by 1, we have to divide the mantissa by 10. All right? That by itself seems really easy to do. We just have to divide the mantissa and then increment e10 and we're done. But remember, we want to maximize precision. That is the part that kind of makes it a little bit awkward, because what we'll do is we separate it into 2 steps, okay? So the first step, okay, let me see here. Oh, that's also wrong formatting. Until e10 is 0, the 0 is supposed to be in the subscript 2. Let's fix that. Exponent of 10. There we go. And the until e10 is 0. Okay. So we're looking for the word until. There we go. I forgot to group 10 into a group so that it will all be a subscript. And to be consistent, let me go back here and fix the n and the d. And by the way, using vi, there's a way to swap d and n by using a few commands. Nobody wants to know, right? But it's a really neat trick, because then I don't have to go through this and do it by hand. Okay, and D. There we go. So I got that fixed too. Okay, let's refresh. Yep, so got all that fixed. Okay. So each step, now we also want to maximize precision. In other words, we want to keep m as large as possible in each step. Okay, so the first thing we want to do before the division by 10 is to say, let's make m as big as we possibly can. Now how do we do that? Okay, we use this loop here. It doesn't look like a loop to me. Well, as long as it's the same thing as while, okay? So it is a loop. So as long as m is less than or equal to the largest numerator value plus 5 divided by 2, we'll keep doing this, okay? We'll keep doubling m, and then we'll keep decrementing from e2. And therefore, we're making the mantissa larger and larger and larger, but every time we double the mantissa, we have to remember to decrement e2 to compensate for the same value. Is that okay? So the key part here is, but how do I know this value? The largest numerator value plus 5 divided by 2. Okay, so how do you find the largest numerator value? If I tell you the numerator is a 32-bit unsigned integer.
All zeros.
2 to the power 32.
Well, I would Google.
31.
I would just Google. There's a constant defined in stdint.h, the header file, that will give you the exact value of what is the largest numerator value. But that's not what you want, okay? Because you want to increase it, you want to add 5 to it and then divide the whole thing by 2. So you will have to take that value, cast it to a 64-bit number, add 5 to it, because otherwise it's going to exceed the range of values, and then divide the whole thing by 2. And then downcast it back to a 32-bit integer. Is that okay? Okay, so let me just kind of do one part of what you can do, or what you're supposed to do. So you want to Google for largest unsigned 32-bit value. Okay, and you can either hand type this by yourself, or you can also look into stdint, because it has that already predefined. So stdint is a header file that is available to you in just about any type of environment. And let me see if it has, yep, there you go. And it's got the maximum value, but it has names too, right there. But it doesn't say 32-bit. But that's why n is in italic. If it's in italic, it means it is supposed to be replaced by the actual width of the integer. So uppercase UINT 32_max will give you the maximum value that a 32-bit integer can represent. Okay? So this can come in pretty handy, not only for this class, not only for this homework assignment, because in many of your other programming assignments and in your jobs, you might need to know how to get to these constants. And they're all defined in stdint.h, standard integer.h. Okay? Nifty little tricks, nifty little tools that can really make your life easier. Okay, so getting back to the notes. There we go. And back to the tab that we were on. Okay, so this is a constant, okay, because this doesn't change. So all you have to do is to keep doing this until you get to m, and until this condition is no longer true, then you get out of the loop. When you get out of the loop, then you perform this operation. Why are we adding the 5 here? For rounding, very good. Okay, so n plus 5, divide the whole thing divided by 10 using integer math, is integrating the rounding into integer division. Okay, so it's pretty handy. So that's how you change m, which is the kind of mantissa influx, because it's partially base 10 and partially base 2. But at the same time, you can now also say E10 is incremented by 1, because I'm adjusting the mantissa already. So your E10 can now increment because I have subtracted the mantissa itself by 10. Are we doing okay so far with this? Okay. So when do we stop doing these 2 steps? You kind of have to do the first step first to maximize the mantissa, do the second step to do the division and change E10. Okay, so these 2 steps can perform as many times as you need, as long as E10 is less than 0. I'm not giving you the overall pseudocode because I want you to come up with the overall pseudocode. It takes me longer to type this than to type the pseudocode. But I don't want to give you the pseudocode. I want you guys to come up with the pseudocode, or the actual control structure in C. Is that okay? So once again, as long as it's the same thing as while. Are we good with this one? Okay. What if exponent of 10 or exp10 is more than 0? What if it is greater than 0? Well, then we go the other way, right? We want to decrease E10 to 0 eventually. So to do that, this is a little bit reversed, because the first thing we do is to divide m by 2. Okay? We divide m by 2 first as many times as we can in order to leave enough space to multiply m by 10. So let's take a look at this code here. Okay? It says as long as, remember that means while m is not less than, okay, not less than, greater than, not greater than or equal to the largest integer divided by 10. The largest integer value divided by 10. How do we find the largest integer value? We just talked about it, okay? UINT uppercase, 32 or 64, and underscore max, I think. Okay. But remember, you have to divide it by 10 because that's what we're interested in. We want to leave enough room to multiply by 10 later on. So you have to use division by 2 to leave you enough space, okay? So what we're doing here is we are doing division, and once again, we're putting this +1 here for rounding purposes. But tag, isn't this going to really mess up m? Because m plus 1/2 seems to be impacting m quite a bit. Nope, m is supposed to be a really, really big number to begin with. We are talking about at least 2 to the power of 32, which is 4 billion something. Okay, so 1 in 4 billion something really should not be that much. Okay, but if we don't do the +1 here, then we have a bias. Okay, the error is always going to be erring on making it smaller. So this +1 is here to make it so that it is not biased. Okay, all right. So, but every time you divide m by 2, you also have to remember to increment e2 by 1 because we want to keep the value represented for the most part the same. Okay, so this is a loop. You keep doing this until m is actually less than the largest integer value divided by 10, because then you have the room to perform multiplication by 10. Okay. So once we have this done, once we get out of this loop, then the next thing we do is fairly easy. We just multiply m by 10 and then store it back into itself, and then we adjust E10 by decrementing it by 1. So you keep performing these two operations. Okay, when I say two operations, I'm talking about this as one single operation and this as the other operation. Okay, so you have to perform these operations as long as E10 is greater than 0, because the idea is to get E10 down to 0. Are we okay so far with this? This is kind of the flip side of the slide earlier. One is to decrease the E10, the other one is to increase the E10, but the idea is to make it 0 eventually. So once we are done with these steps, the next step is to normalize the mantissa. So the mantissa needs to be normalized because it may not be doing the the mantissa at this point is a really big unsigned integer. Okay, so normalizing means we are moving the binary point so that it becomes 1 point blah 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 blah. But there's no actual operation that you need to do because we can do all of that by just adjusting E2. Okay, so that's the idea, is when you have, okay, let me switch to the document camera. So when you have a number that's kind of like 1 0 0 1 1 0 1 1 1 0 0 1 0 1, okay, it doesn't even matter. Okay, the implicit point is here. In other words, this is what m looks like. When we are done with all of those steps, m becomes m2, but this is what it looks like. Okay, the binary point is all the way to the right hand side. But we'd like it to be over here. Does that make any sense? But there's no need to really do any shifting because I don't want to really change the representation. All I need to do is to account for the number of shifts that is needed to move the binary point from here to here. So now I can say this thing is the same thing as 1.0011 blah 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 times 2 to the power of what? Well, we just have to do some counting here. Okay, so you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Now, in your case, you'll be adding 13 to whatever EXP2 already has, or E2 already has. Okay, because we're just shifting the binary point, and every time you shift it by one place, you add 1 to the exponent of 2. Is that okay? All right? Okay. So in order to do what we need to do, we're going to do these two loops because we want our mantissa to have exactly 53 bits, including the 1 point. Okay? So that means before the normalization, if M2 is using fewer bits than 52 bits, let's pump it up. Okay, so we'll just keep multiplying M2 by 2 and adjust the exponent accordingly until we fill up exactly 53 bits. So it becomes 1 point something something. Okay, with 52 bits to the right hand side of the binary point. What if we have too many bits to begin with? What if the current M2 requires more than 53 bits to represent it? Then we downsize it until it can fit within 53 bits. Okay? These two loops, you don't need an if and an else to perform these two loops, because your current condition, there are 3 ways for your current condition to go. It's either this, where you go through this, but when this loop exits, it should not get into the second loop. Or, you don't meet this requirement, this loop doesn't execute at all. When it does meet this requirement, the second loop runs. Or, ideally speaking, it doesn't run this nor this, because the value that you have is exactly using 53 bits. Then you don't need the first loop nor the second loop. So these 2 loops can be performed sequentially, and it's not going to mess anything up. Okay. Are there any questions about this part? How do I specify 2 to the power 52 in the C program? Remember, you cannot use power. You cannot use anything that makes use of the double type.
It'd be 1 shift left by 52.
Yep, there you go. Same thing with the other one. 2 to the power 53 is 1 shifted to the left by 53 times. Okay, very good, good job. But you have to be, but this time you have to be careful what the type is for M2. Okay, because in order to do all of these shifting, M has to be a 64-bit number. If M is a 32-bit number, the shifting will give you a 0. Okay. So when this is all done, we guarantee that M2 is between this and this value. Then it's just a matter of adjusting E2 and masking bit 52, turning into a 0 to get the fractional part, to only have the fractional part of the mantissa remaining. Okay, so are we doing okay so far with this stuff here? Okay, I'm going to stop the lecture for now. And I have another case here where I forgot to group it. This is supposed to be 2 to the power 52, not 2 to the power 5 times 2. Okay, so I'm going to fix that. But other than that, are there any questions? Now over at the lab, I'm going to give you the solution to the subtractor, but this time I will use the multi-bit approach. So for those of you who want to know how to use a multi-bit approach to the homework assignment, you can go there and watch me do it. Otherwise, this is your new homework assignment, and you can get started on this one. And I'm going to fix this first. You guys can leave the classroom while I'm working on this.
So, is our homework assignment the parser or that? So our homework assignment going to be the parser or the one that you were just lecturing on?
Parser.
Okay.
Just the parser. The parser part, will take some people about a week to get it done, and then after that will be the portion that we just talked about. So the homework is lagging behind, which is the way it's supposed to.
Should we do the parser one in GDB?
In GDB?
Or like using BI, whatever.
I have not set up accounts on the Power server for this class, so we will use the usual way, which is code blocks to do it.
And make sure we hit the file in C and not CPP.
Yeah, plain C and not CPP.
How do you set up your own like server like that, like to do your editing and stuff all in the terminal?
This is actually my home PC.
Oh, okay.
So I just have my router set up to forward port 22.
But how do you do that? Like the whole, like all the stuff you have set up to do like all of your editing stuff on the terminal?
Yeah, I just have to install certain packages in Debian.
Okay.
What would be the difference?
Oh, it just means that we use splitters, like you can look at the